entitled Hybrid Renewable and District Energy Systems. Once again, so little housekeeping things, we do have little surveys on each of the tables, so if you can fill those out. And as I was looking at them, I did notice that 1 is good, 5 is bad. So if you're filling that out, keep that in mind. So, but our presenter will be Cary Smith. Mr. Smith has been in the energy business for over 35 years. He's a founding principal of Sound Geothermal Corporation. Sound specializes in the design and verification of energy-efficient HVAC systems. Their projects range from HUD housing to industrial facilities. Sound Geothermal is one of the pioneers of geo-exchange hybrid systems in the western United States. Mr. Sisler serves on the IGSHPA Standards Committee, the Training Committee, ASHRAE Technical Committee, 6.8 Geothermal Utilization, ASHRAE Technical Committee 9.4, Applied Heat Pump and Heat Recovery Systems, and serves on the Utah State Board of Trustees for the Association of Energy Engineers. Cary is a certified geo-exchange designer, certified energy manager, and a certified energy auditor. So, can you give a hand to Cary?
Good morning. We're going to take a look here at kind of applications for renewables and conventional energy. One of the big problems we have with renewables in general is that they're expensive, and trying to get the life cycle cost of the system to come out to the point where your customer, your client, or whoever wants to pay for the thing is sometimes a little bit difficult. But there's a lot of really good engineering reasons why we want to look at these combined systems. And we'll go into some of those as we start. Just as you heard, I guess a little background, I've been in the energy business since 1972. We're still in the energy business. We started out in oil and gas, and then went to a little bit of high temperature geothermal that we were joining out in the western part of Utah. And then went from there into, we got a little introduction to low temperature geothermal, which is ground source heat pumps in the application. And we've been kind of working our way through those systems and trying to do innovation and stay a little bit on the cutting edge for what we've got. So from a national standpoint, some of the things we're going to talk about today when we talk about combined energy systems, well, that's starting to get a little bit of legs, and from a national standpoint, district energy systems. So we're going to kind of talk about some applications of those and why we want to use them. The presentation we're going to talk about a little bit, start out with some hybrid GX or hybrid geo-exchange, and then we're going to go into the community systems, and there are a couple of examples of the systems that are out there. Just for those that don't know or haven't heard about ground source and stuff, basically we're using the earth as either a source of energy or a repository for energy. So in the summertime or in air conditioning mode, we put energy into the ground, and in the wintertime we take energy out. Well, that's okay as long as you have a balanced season. But when you are in kind of in an environment where you're cooling down, eventually your loop field is going to get hot. As it gets hot, the efficiency decreases. And the same thing for high altitude. When we start looking at Park City, some of the stuff we've got up on Wolf Creek, Daniels Summit, Jackson Hole, and so forth, well, pretty soon we're heating so much that we run out of energy. So we've got to have a way to turn around and look at that. How do we turn around and balance it? And how do we keep the flow, if you will, of the energy into the optimum, and the fluids into the optimum range for the heat pumps? If we can do that, we can increase the system COP significantly. So this is all about turning around and taking a look at these systems instead of components, looking at them as systems. From the systems, we can turn around and determine that system energy, the system exergy. Okay, a hybrid system is a heating and cooling system that couples renewable energy systems with conventional technology. Pretty simple. Examples, of ground source heat pump that uses a loop field or a water source. We couple it with a cooling tower in a cooling dominant area, or a boiler in a heating dominant area, or solar. And solar thermal seems to be one of the really good makes to this technology. And what we've got is, let me see if we got it. I don't. different types of energy. We have this a pump and re-inject system. We use this in Utah. Usually used where there's a good aquifer. In the state, we consider that to be a multiple use of the same resource. So we've been having very good luck in terms of permitting those projects. There's a little bit that's going on inside the Salt Lake County, where we're having to turn around and sit down with the utility people and identify where the aquifers are, the potable water aquifers, and make sure that these systems don't interfere with it. The next is the conventional ground source vertical. This is a pond loop using slinkies. And then we're going to couple them with boilers, or a tower or fluid cooler, and then we're going to use solar heat. So these are some of the things that we're going to look at real close today. Why would we do this? Well, the lower first cost is really what we're going after when we first initiated these things. You know, we were starting to look for a way because the municipalities and the clients were kind of blocking at the first cost. The bigger systems were coming in a little bit cheaper than the conventional systems if they went to the high end with the same type of comfort, conveniences, and so forth. For example, a VAV system. But when we started moving into the smaller schools, smaller buildings, and everything else, it was tough to make the thing come out. So we started looking at the potential to couple this with conventional systems. Well, what we found out was that it had a lower life cycle cost. We ended up with longer equipment life because we're sending a more optimum fluid to the heat pump. So it, like gas, doesn't have to struggle to get to its capacity. Lower emissions at the point of use. This is starting to become a big issue. I just got back from Washington, where we were sitting down and talking with our senators and senators from 18 other states and congressmen, and we're talking about how we can turn around and integrate renewable technologies and start to take and identify the benefits we have when we move the emissions from a populated area, read that as the orange cloud over Salt Lake City, and we turn around and start to use non-combustibles. And that's about 40% of the air pollution that we see. So they're starting to get a little bit of legs there. We're starting to see we spend billions and billions of dollars in end-of-life care, most of it due to respiratory illnesses and stuff, about 80% of the dollars that we're getting in here. So Medicare and Medicaid. Give you an example, why does this link together? Well, about 5 years ago, 7 years ago, we started in the state. Our portion of the federal funding went from 7% to 14%. In the next 5 years, we're estimating we're going to go up to 21% of the state budget is going to be used for complementary medical assistance and care. And again, if you remember, respiratory illnesses is one of the big culprits. So lower emissions at the source. When we start to look at things, we call that the exergy, the total energy, total carbon footprint. The big one, reduction in water use. On a high school in Las Vegas, we use about 4 million gallons a year. Most of it goes to the, believe it or not, to the sports field. The rest of it is either consumed by the patrons or it's running the HVAC system. We were able to reduce water with hybrid systems by 25%, million gallons a year. When we looked at city center, using heat pumps to shuffle energy around, we were able to turn around and save them $1 million in the first 30 months, and a total of 120 million gallons of water a year out of the 600 million that they were looking and anticipated. In Las Vegas, about 100,000 gallons to a home, so we're equating it to available population and resources. And then we turn around and we start to find out, as we play with this a little bit more, the geothermal well field becomes sort of a really neat thermal storage device. Actually, a pretty good one. This is a typical hybrid system. If I'm going too fast or whatever, just somebody holler. We have a well field that's tied into a building loop, and we come up here to use the heat pump to take and move the energy in or out of the building. And in the cooling side of it, when we're trying to get rid of excess energy, we might send it out to a tower or a fluid cooler. Pretty simple. But what did we learn? And this is some research that was done by the Geoheat Center and stuff. But when we started looking at all of the temperate areas across the globe, that 50% of the building load will handle you for 90% of the hours a year. We stop and think about that. Why don't we turn around and apply our technologies where they do the most good, at the right time? This is a bin table. It's kind of neat. We have our months starting down here in the heating and going up to the middle of the year. July 17th is about our peak day here in Salt Lake City, and then as we start to come down. But when we turn around and look at the number of hours a year on a hybrid system, using that same formula that we have, about 50% of the load of the renewable sources or outside air economizers will handle you for about 7,217 hours a year out of 8,760. That's pretty significant. We can use the highest efficiency equipment for that portion of the year. And then we got to add a little bit. In this particular example, we're adding a tower in the summertime for about 760 hours. We've got a system I'll show you later. It's the total runtime on the coolers. It's down in Las Vegas. Total runtime on the coolers of the year is about 400. And then we need a boiler at the end to turn around and handle it. We either bleed it in, we start to supplement the system. The general idea is to keep the temperature entering the heat pump at an optimum level so we get the highest coefficient of performance and the highest energy efficiency ratios. Think of the ground loop as the thermal storage system. Well, if we got that, we found out that we could do some load shifting. We could start to play with the cost of the system and the cost of the operations of the system. So we started moving energy into the ground in the cooling dominant situations and then taking it out at night. And we're going to get rid of it. Well, what happens in our dry western climate is at night the wet bulb drops, the temperature drops. We can turn around and reject more energy through the same piece of equipment. And that turns around to be a significant advantage when we hit the building in the beginning of the day with a cooling load. So when I go into, we start to pre-cool, and almost all schools and stuff will do this. Somewhere between 5 and 7 o'clock in the morning, we can turn around and we can hit it with, technically, a native earth temperature, about 72-degree fluid. Our EERs in that case jump up to somewhere in the neighborhood on conventional equipment, 16 to 18, on high efficiency equipment, as high as 28 EER. And the pre-cooling, used properly and set up on the proper time, is going to save about 10% of the energy cost for pumps and towers. And that was done and verified in a DOE study by Scott Hackle and Energy Center of Wisconsin. And we worked on used two of our projects to turn around and take a look and see how we can quantify this into the new ASHRAE software that does hybrid geothermal. Okay, we started talking about that. We got the hybrid part. Everybody kind of got a pretty good grasp on that? I don't see anybody falling asleep or rolling over, okay? Now, we start to look at this. The next thing we started to think is gee, if we can turn around and use conventional equipment, why don't we just shuffle the energy back and forth between the buildings? Let's only kill that dinosaur once. And then let's turn around and reuse the energy we've already paid for. It's going to cost us a little bit of a transport fee, but why not? Well, assets are other buildings now. Potable water delivery systems, community black water systems or gray water systems, and solar assets start to come into play real well. Include panels, tubes, or even an area with hydronic tubing in case of a wall, patio, or snow melt system. Wow. Maybe we'll get snow melt to pay for itself. I don't know. That'd be a long stretch. Okay. In a community hybrid system, we have 3 or more stages of transfer. We call these, or we're calling these, just kind of a marketing way to go and present it when we sit down and talk with it as the least energy path. What's the least amount of energy we have to spend to get it from one place to another? Well, the first thing is that we design the building to share energy with itself. We'll see that a little bit. Then we'll start to share the building energy with other buildings. So if we have a classroom where we're air conditioning, we're rejecting that heat. If we put it in a transport system, we can take it down to the dorms or the student center or the laundry or the swimming pool, and we can turn around and heat those areas. So the only transport energy we have is a pump, and that pump is we're going to optimize it for part load too. So we're starting to talk about the system. This is really the key that we're trying to get to the engineers. I think that this is going to be an event we're going to see ASHRAE going on here for our Mechanical Engineering Society, that we're going to start looking at system efficiencies rather than box efficiencies. Anyway, the system calls for assistance from a renewable source. That could be the loop field or a solar. Then finally, the system calls for help from conventional equipment, a cooling tower or a boiler. Give you a little example of how it flows. Stage one, we just move the energy around the building. So if we have in the wintertime, if we have a perimeter that's heating and a core that's cooling and stuff, we just move that energy back and forth. And there's about 25% more energy available in the cooling side, because to take to the heating side work, we can now include the heat of compression as part of our transfer. And we could in the building, but we can also take that. So the ratios of what we need to do these times becomes a little bit something you really want to look at. Well, stage one. Stage two, let's just use this central loop system here we've got to start sharing energy with the building. This guy's all in heating, and this guy's all in cooling down here and stuff, and we can start to see where we can share that energy around through this, using this transport loop we've got. Finally, or next to last, we'll call into the central loop calls for bore field, hot or cold, and maybe solar thermal or renewables are now kicking in. And these are ultra low head loss designs and stuff, so we have very small horsepowers that we're dealing with. And then finally, we'll go to the fluid cooler or the boiler. And just to give you an idea, there was just some fun numbers we have up here, general ideas. Everything is controlled by temperature now. And we're looking at the building, we're looking at global systems. Well, almost any combination of buildings works and stuff, and it just depends on where you were. And those are two words you're going to have to learn. To do any renewables, you have to learn these two words. It depends. Because each case, each site is dependent upon what those particular assets of that site are. And if you can turn around and organize that in your head and get it down and start, all kinds of things start to drop into the design. But dormitories and hotels are just really great systems. And usually the bigger the system, the more opportunity there is to do nothing but share energy back and forth between the buildings. Tulsa right now is getting ready, I understand, to start a community district system at the government buildings in the heart of town. They have different times they operate. Some of them stay open late, some of them are, they'll shift the number of people they have, or computers, whatever have you. But the energy use is different in those buildings, and we start to look at that. Well, all of a sudden, from a design standpoint, what we've got to start looking at is 8,760 hours a year on our heating and cooling loads. No more sledgehammers, no more peaks. We've got to look at hour by hour so that we can turn around and take a look at what available energy we would have at any position along the time of the day so that we can optimize the design of these systems. That one was installed. It's a black water heat exchanger. It was pilot tested here in Salt Lake City at the Downey Mansion, which is about 8th and South Temple. We made a deal how to sit down with the utilities people. We used a stainless steel heat exchanger, tube heat exchanger to replace the sewer. So, guess what we're feeding the energy to a lawyer's office with? And what do you think might be the source of that energy? Because we're just below the university. But think about the permutations. We have a 12-inch pipeline across the street running absolutely full of black water. We haven't touched it. District energy systems. How about using the assets we've got for anywhere? There's a fountain heat exchanger. This is used a couple of places in the city, and Las Vegas in particular, and stuff, the big fireworks, waterworks you see. A lot of times those are supplementary cooling towers. If you look at the casinos and what they're doing. Solar thermal heat exchangers all of a sudden start to come into play really well. And one of the best applications here is a closed-loop geo-exchange system. Why? Well, you want to look at the solar thermal and you ask yourself where, when, and how. On the where and when, well, let's think about this. When the heating degree days exceed the cooling degree days by more than about 20%, that's an arbitrary number, and stuff, I've got a net negative energy or pull, net taking extra energy out of the ground source, so I have a life to it. If I were to take a little bit of solar and trickle charge it, or turn on and feed it back into the loop, then I could restart almost every year, couldn't I? I could actually set the system back to normal or native ground temperature, the most optimum temperatures for the heat pump. If you have a high use of domestic hot water, hot processed water, district energy systems require energy during the winter months. Natatoriums is a good one that are going to take a lot of extra energy. And in some cases, we're starting to see this show up in the solar calculations in the software, the solar panels at night actually being used to reject energy. And usually that's for a very low horsepower, a couple of watts. It could be DC. Maybe we'll tie some PV into that. But we'd have to have battery storage then. But even so, there's a lot of times that we may be able to turn on and get just enough off the top to get where we need to go. It's optimization. And solar thermal. And anybody that's dealing with solar thermal knows there's a cost of system efficiency. You're going to try to take it. The more you try to take, the less efficient the system gets. Actually, the bigger, if you put a panel too big an array, you can actually get to the point where you're losing efficiency of the whole system. Well, if we turn on and take that and use that extra energy that's just kind of sitting there and wasting it, we may have a whole different system efficiency curve, as it's shown right here. And here's the gist. Anybody that's done solar looks at this. What's this? This here in particular is the waste energy. If you're satisfied, the hot water tank's already satisfied. So, well, gee, see how this works. Stagnation or storage. In a conventional solar-only system, that would be a stagnation point. You do a drain down, you cool it down, you wait for the hot water heater to say, I need more energy. If nobody uses it over the weekend, all that power is going away. All that energy is going to waste. And this works in the shoulder months best. Don't think of it just in the summer months where you get this stagnation curve. On a weekend in a school, you have the same curve, but it may come up in the middle of the day in January. We have buildings that we see on these systems right now we're watching on a day-to-day basis where the temperature that we're seeing on the solar ground source combination system is 61 degrees, where normally it would be somewhere around 45. So we've got much more energy available. Okay, well, what else? Well, now we have to say about how. Where do you put the solar energy? How do you do it? There's one guy says, I'm going to put it on the load side. One guy says, I'm going to do it on the source side. Well, there's that buzzword. It depends. Load side, where the partial load heating is needed and the lowest energy path is without compression. Let's think about that. We're using the solar energy, what we stored in that tank or whatever we do. Instead of running the heat pump and running a compressor, we turn it over on a smaller pump and take a little bit of energy out of that tank and take advantage of the solar energy we have. How about the source side, when the thermal energy storage is needed to increase the heat pump performance in heating dominant situations? Park City is a good one. If you're doing any of the super homes or looking at any of the super homes up on Wolf Creek, 9,400 feet, guess what? That's a heating load all year long, except for a couple of days. So why don't I use my solar system to help recharge? Here's a low side system, and what's happening right there is that the solar collectors are feeding the storage tanks and stuff, which feeds either the hydronic heating or the domestic hot water system. We're not, here's the source, we're using these two heat pumps to turn around and supplement everything. So, but really the load side is taken up by the thermal storage, or the thermal storage from the solar is taken up on the load side. A little less clear drawing, but here's one for the source side, where the solar system here is actually going over here and is being used to supplement the ground source. And it also has a direct tie-in to the load side of the domestic hot water. But generally what we're doing is we're taking our energy into the ground if we have too much available to us. Snow melt systems, good or bad? It depends. Everybody got that? It depends. You're all solar or geothermal experts if you didn't. Can be used as a passive solar collector any time of the year that the surface is exposed to the sun. Jackson, or in Steamboat Springs, the old hospital property, 4 acres in the middle of town, when they plow the streets on the black asphalt, mid-December, another spot where we were seeing 60 to 70 degrees in the hydronic fluid that's going through the snowmelt tubes. Why not take it back to the ground source? And let's increase the efficiency of the ground source by moving that energy in the wintertime on that nice clear day through the snowmelt system. Well, gee, if you do that, why can't you air condition with it? We're using this system, we calculate out the energy, and it just becomes a horizontal loop. The snowmelt system becomes an energy rejector. So we took a little bit of the head off the kind of negative impact of the snowmelt. Not all of it, but a little bit. I mean, you're talking about 125 BTUs per square foot to melt snow. Our area, something a whole lot less, 15 to 20, to do the same thing in the home. So it's, you know, it's one of those things that we have to deal with. But it's also a health and safety issue in schools and loading docks and things like that. Central loop distribution. We have 2 different main types. One's called a spider web. We did that just to keep away from saying the word central plant because it has a whole different connotation to it. Because we can do distributed energy from the central plant as well as you know, treated fluid from the central. So we can use a central point to turn around and take the earth loop fluid and solar renewable fluids itself and distribute them to the buildings. Or a regular central plant would turn around and maybe make energy with a boiler or a cooling tower and send either chilled water or hot water out to the buildings. So we're still using the heat pumps. The district loop is the larger packages. We get large campuses, and we'll show you one here in just a second, and stuff where we've got to transport over multiple city blocks or distance. You know, and the same thing goes. The buildings share energy, the loop fields are staged in, the hybrid assets are staged in. It works the same way. It's just, it's really not very difficult. It just takes some thought to plan. A couple of case histories. Cashman Equipment, Henderson, Nevada, 7 buildings. It's got a central plant system. Now everybody's going to glaze over because I'm going to show you some pictures and there's schematics here. Don't panic, we'll just work our way through it here. But here's the facility as the renditions of LEED Gold facility. It was one of the studies that went on the DOE application we told you about a little bit earlier. So as we've got a lot of really good data on this particular system. The central plant is located about in here. There's the well fields that go in under this place and back under here. This, by the way, is case hardened to support the weight of a tank, because the D9 is so heavy that it's turned on, we don't want to see. So that's like 4-foot thick concrete on the pathway. The interesting thought is, you know, it's just what do we do? But we have that D9 has to be completely cleaned before it goes into the shop, because the least amount of dirt might be on the system that they get into the engine and stuff while they're working on it and stuff. We put that $100,000 or $200,000 engine down. But we've got 65 miles of high-density polyethylene pipe buried in the ground. We've got 3,100 total square feet of new construction. We did a hybrid geothermal of 60-40. That means we took 60% of it in the renewable side and 40% on the conventional side. About 144,000 feet of borehole, and it gives you the rest. And we're dealing with about 2,100 tons of cooling. in the system, and just give you a little bit of idea of the magnitude of what we've got here. When we did the pre-modeling for this, we started out the lowest annual operating costs, and actually we're below these estimated levels right now. We're running more about the $325,000 number, so it's working better than we thought it would work, which is good because it keeps us in business. And then we also turned on and look at annual energy and peak kilowatt savings on energy. Again, the ground source system came out ahead. Field schematic and stuff, the neon stuff is where we put the bore fields. Each one of these little boxes represents 15 boreholes. Stuff we're coming back into the central plant, that we're distributing it out to the various buildings that we've got on the system. We originally built a mechanical room that was like 40 by 20. And right now you walk in and it echoes. To give you an idea of how much room in here, we even get the piping of what's going overhead. But this particular system has ground loop covered with closed circuit fluid coolers, type of cooling tower. But in that particular case. So what we have is we have a central manifold. That translates to our central loop, removing the fluid out of the bore field from here, and we're turning on, we're either taking it to the buildings or from the building, and we're going, if we need it, we can kick in on our primary, secondary pipe. We've got a crossover for night cooling and stuff, some of the things that we talked about. I don't want to go into a lot because it just, it's not going to make as much sense to you as it does to me, but generally, this is the central distribution system, and it's about a 14-inch pipeline inside the building. And then we have the loop fields on this end over here. Give you the schematic. We've got the loop fields, which we're supplying, and of course we're recording, as you can see, all the temperatures in and out, and trending all this data so that we can go back and retro commission the building. We can redo it if something doesn't work right, or it's not going the way we designed it or the engineer designed it. We can go back in there and trace it. We can see what's happening. One of the most important things you can do on any system is track it, set it up so that you can turn around and get your data and look at it a year later or over the seasons as they change. And on the other side of that central loop, over here, we've got the building. And the way this is set up is that the first stage is we're sending energy to the buildings, or we're sending our fluid to the buildings, but it comes back, it has the first opportunity to circulate inside this subloop. So that's how we turn around and we look at the building. So we don't turn the well fields on unless these loops and temperatures of the fluids going in and out of the building are either under 50 degrees or over 85 degrees. So we just let that stuff go round and round. And the different buildings do whatever they need to do, or take the energy out, or put it back in. And until that whole central loop system comes up to that, in those above or below those ranges, we don't go back to the loop or the cooling towers. Let's take a school. This is probably one note. We're getting some new data. This has been going on now for 2007 is when we started this project. We've had it on a global control system now since Thanksgiving a year ago. So we've got about 18 months worth of data in this, that we're fine-tuning this looping system. But when we first started, we went down there to do a thermal conductivity test on the system for one building. And that was a classroom building. So that's our industry's black box. We're turning around, we're putting a little energy in the ground, we're measuring how fast it takes it, how much energy is absorbed by the ground at what rate, and we're coming up with a thermal, and from there we can calculate thermal conductivity, diffusivity, and also, most importantly, we can see what the deep earth temperature is, what our native temperature for the ground. Well, the results of the thermal conductivity test were very good. So we turned around and said, okay, well, gee, this is great for the western slope. Partially because we're in downtown Grand Junction, and we've got 90 feet of river cobbles and rocks. And then below that, we have a high-density shale called the Mancus. And the shale in particular is an excellent heat conductor. So We have a good resource, good storage, everything's working out. Well, we get into, we're starting to talk, we present this data, we're starting to brainstorm about the site. Then about the same time, we were asked to design a similar system because they said, you want to run another thermal conductivity test for the new dorms we're going to put up. Well, wait a minute here, you got dorms, the classroom building. Doesn't that sound like one of those perfect matches that we talked about? And we went to the engineering company, the mechanical engineering, we sat down with them, we brainstormed together, and we came back up with, started saying, we're going to push a central loop on this thing because we found out there were at least 9 other buildings planned to be built in the next 5 years. Well, shoot, what a perfect opportunity to do this because we're going to be messing up their quads, we're going to be messing up their streets, they're starting to enclose the campus instead of having the traffic go through it and stuff, so we have access to the utility corridors. What a great idea. Well, the 6 buildings are getting built, and it actually is more now. So why not link the buildings? There's a picture of the campus, and the first building we're gonna build here is down in this area. We have the southern part of this campus right now is on the central loop system. We're just now getting ready to doing the planning for the central loop system for the northern side because they found out that at the time they were building the Saunders Hall, the gymnasium and Olympic pools that they had in there, that it's getting pretty expensive to heat those pools with the gas, and we're having to heat all summer long to turn around and keep the humidity and balance inside the natatorium. Well, we proposed a central loop, and the first one looked at we were going to do about 1,500 tons and about 450,000 square feet. And there's we call that kind of a hairpin. This is the first take on our central loop system. That was going to be an 18-inch pipeline, and it is an 18-inch pipeline right now. So then we turned around, we stubbed out to turn around and make sure that we could pick up the campus, North Campus at a later date. We wanted to add these new dorms in here that were going. We found out there was going to be another set of dorms that come up in here, and they're there now. And we're getting ready to look at dorms on the north side of campus and stuff. So what we're doing is moving this energy around. We're going to find out what building. So we were tasked by the university to come back in and give them a program and track the changes. At that time, we also had a company come back and look at the energy analysis that was done for the campus and look and determine what our baselines were. So we knew what we were telling people was working, and we knew that what our changes we made could turn on what are we gaining on this system. And there's your central loop. We kind of changed it to a hairpin, and then we did a little leg off of this. So this is a primary single pipe loop and stuff, and we've got another secondary, if you will, primary second loop. We put this is the Science Center, Woburn. You'll see some numbers and pictures here. The new part of this is where we put the main pump station for the central loop, and we decided to put the auxiliary pump station down here on this loop. So it's all set up and valved that we can turn on a pump with either side. And you know, obviously we figured we would have to have somewhere in the neighborhood of 5,000 to 6,000 gallons a minute at peak going through this building. Kind of one of the fun things we'll see here as we go through is we've never gotten over probably about 3,500 gallons in that system. And right now it's idling along at we've got a 40 horsepower pump on the main side. We're at 30%. So do the math, we're 8 plus horsepower that we're using to move that energy. Then we turned around and we said, well, if we're going to do this, we have to have a way to control it. We have a way to measure it. So we went out and we started to take, because each one of these buildings, as it's kind of the hot pot. One's got Johnson controls on it, one's got ALCs, and it's got Allerton, so they also got Train and stuff. How do we make all this stuff? We don't want to be switching back and forth between a bunch of programs and stuff. So how do we put this together? Well, it turns out there's a system that was developed exactly for district energy systems. And I'm going to say today, I don't think I have a restriction here by telling you, it's a train system. We don't, I'm going to say I don't much care for the normal system they use inside of a building. I find it too proprietary. But this new system is very good because it turns around and it reads everything. As a matter of fact, when we were doing what we call our controls fair, where we invited different vendors to come in and show us what they could do, Train took the time to take the Allerton system, or I'm sorry, the ALC system that was in our building that we were giving the demonstration in, and tie it into their system. And it took them all of about 30 minutes to do. So what they did was they presented not just the system where they could read the train tracer, the tracer summit from the 5 or 6 buildings they had. We could also pick up the ALC building that we were looking at. This was a hand-down, no-brainer. Handles hundreds of thousands of discrete points that we can measure and control. But this is a picture coming off the system with temperatures, and I grabbed one here just the other day when I was working on it. So they're pretty mellow day. It's about 63 degrees. But these are distributed loop fields around campus. This is where those dorms are. And these are those big standby pumps or secondary pumps I told you about. Our main circulating system is in here, in the Wooded Hall, the student center's attachment. Well, what's happening here? I got 65 going into the building and 68 going out. We're in air conditioning on that building. At 61 outside air temperature. In Woodman Hall, when we start to mix all the goodies, we're 66 and 67. Pretty balanced. What do we got here? 66 and 66. I can't see it. I got to go through that. But this is Houston Hall, and we're going to see a little piece of that. But on around the 18-inch pipeline, which is this goal, to the dorms, what's happening? We're seeing a bit more activity in the dorms. Both these pumps are off. This pump is on, the ones that are green. And so we're telling what we're doing. We get a quick visual on what the system is doing. Dormitories, classrooms, and student center. Don't glaze over. Houston Hall, well, is the existing mechanical room. We had some boilers. What we were tasked to do was utilize all of the equipment the college had already paid for until the end of its useful life. In some cases, that was stuff that was just put in a year or two ago. In the case of these boilers, they're about 12 years old. So we wanted to do that. We didn't throw anything away. We didn't have to. But the real interesting thing, we added the central tie-in to Houston, which permitted us also to go to the East Campus. We added one new bore field. We've got stub outs for a second new bore field, but sometime later when we bring more of the buildings on. And then we're using a heat exchanger now in a separate system to couple the boilers to the central loop. So now we've got those. And we retrofit everything inside the building with water-to-water heat pumps, fan coils, and chilled water coils. So we're doing everything with heat pumps now instead of boilers. We are touching the system inside the building on some of the fan coils that required higher entering temperatures. So we didn't have to change those out because they had just been replaced over the last 3 years. But they're set and we're designed to be able to take the 120 degree on the new equipment. Here's that Woodman Center, the central loop schematic, and what we've got is here's the central loop pumps. Right now we're idling along where our speed is 33%, so a little over 20 hertz. And then we've got a chiller that's available that was already in the building. We put a new fluid cooler or cooling tower for the central loop system. It's a 500-ton tower. And we can get to actually sit with some of it here. We've got the existing boilers that were in Woodman that were almost 20 years old, but they didn't want to take them out. So then we have the building, so that's adding to part of our loading scenario. And then the second 150-ton tower that was there when we started. So there we are. And then we added one more thing. What am I missing in my central loop? How about a way to look at my demand or my consumption? We set up a button. Tri-State Generation has a program where they'll call their major industrial customers and they'll tell them that they were having a load event, usually in the middle of the summer. And the first time this happened while we were under construction, the building facilities manager, Kent Marsh, sent his guys, had to gather them all up and then send them scrambling out around the campus to set back thermostats, to turn off outside air, to do anything they could to limit the demand, because he was told if he could limit the demand in the next hour, then they were going to send him a check for $5,000. So we got out there, we watched these guys scramble around, and we said, hey, we got a better way to do this. Let's put this button on here called global demand limit. What we've got is with one click of the mouse, we can set back every building that's attached to the system and is attached to the control system. So some buildings that are not yet attached to the geothermal system, but are attached to the tracer summit and to the control system, we can set those buildings back. We can do global demand limiting. The story goes that, I don't know how true it was, I wasn't there, but I was told that, there's no reason not to believe it, that when Kent got the call, he hit the global demand button. We never, other than exercising it, we never really done anything to measure with it. And 15 minutes later, Tri-State could see the reduction in demand, 230 kW, just that quick. So it's a huge tool, and at that, we're now looking at a sum for all of the buildings, and the size of the demand limiting we did at somewhere between $5,000 and $10,000 was the bonus check you got. Here's a kind of a pictures of the campus to get a feel for what we are. This is the classroom building here that started the thing out. We have a loop field under this quad here. We're looking up north into the campus, and this is the old science center. And we ended up putting bore fields all the way in through here. Here's Rubin Hall that we saw the stuff we were using, the cooling tower on the roof, and some boilers there. We're drilling out in front now. We come back down, we've got the library and Houston Hall that are tied together, and these are those old boilers I told you about that we had to take up on the loop and stuff. And then we move along the bottom part of the loop, the southwest corner where the dormitories were and stuff. We've got more loop fields that we have set up, and here's some of the main central loop stuff going in and stuff. And then we go up to the Fine Arts Center, which hasn't been tied in yet, and we've got a field where we're putting loops back to where we started again. This guy's got a cooling tower on top of its roof that will eventually tie into the system if we need it. And what we're planning is now the next 2 blocks up for another 1,500 tons on the next part. And we will join the 2 central loops together so we can now trade energy from one end of the campus back to the other end of the campus. Current project size, 980,000 square feet, 2,400 gross tons. We've got there's planned for 205,000 feet of vertical. We've only got 165 in right now, and it's behaving. So we're really thinking, how many buildings? What do we do? This is where that modeling comes in that we told you about, where we're starting to look at that 8760 loads for all the buildings we had out there. We're starting to look and see what happens that we can pick up Saunders Hall, and the major gas hog that they've got right now is the swimming pools. There's 2 of them. So anyway, this is kind of out of date, but the estimated annual energy savings is $480,000. Kent says we're on track. There's a bounty, I guess, or whatever you have, an incentive from the state of Colorado for about every 2,200 tons of carbon reduction that the facility goes and presents to the state and validates to the state. They're going to get $100,000. The central loop system in its entirety cost a little over $480,000. Looks like we're going to get most of that. That's just coincidental. It looks like we're going to get most of the cost of that central loop back in the first year between the demand limiting and the carbon reduction from the state. So anyway, this is what we are. I think this is the status of the industry. We're moving it forward day to day. We're looking for ways to turn around and use DC pumps as things get better, PV, whatever we can integrate into these systems. But it's truly a case where the system is more valuable than some of its parts. Questions?
What about relative humidity, 10% compared to 90% outside here? How does that affect personality?
Well, and the question is how does relative humidity?
Does it affect, I mean, if you're in a 10% dry desert as compared to 90% East Coast climate, how does that?
It's a good question. And what happens is you design the system for the wet bulb and what you're going to look at. And that's pretty much what you're going to see on a heat pump. I mean, we use heat pump systems in Florida. And if we're going to do any rejection, we have to figure a way to take care of that. Obviously, a cooling tower or evaporative cooling device becomes less and less important. But do we start with airside cooling? Do we turn around and look at thermal storage? In Las Vegas, we're taking our part of our demand, as I told you, we're stuffing the energy in the boreholes at night, and then when peak demand is through and our rate drops to about 2.5 cents from 7 cents, we reject all that. So all of those are calculations that have to be made. Right now, it's working just fine here in Denver, Oklahoma City, Tulsa, Minneapolis, Phoenix, Las Vegas. I don't have anything that we've done in Florida yet, but you know, parts of Texas. Don Penn down there has been designing some energy stuff in Texas, and has got some stuff in Houston, and those are hybrid systems. I don't know exactly his configuration, but it is important that we find out. How would you get rid of the heat anyway? What would you use to get rid of the energy in the air conditioning side? Air conditioner, air side. We're going to use the water instead of the air. So we may have to go to an air side. Anybody else?
So, in theory, a good contractor could take systems that are already in use and create a hybrid system like that?
Yes. The question is could a contractor retrofit an existing building with a hybrid system? Yes, we would utilize those assets. You may have to change some of the prime movers. Back to the it depends. If I get a central plant, it may be economical for me to turn around and change, or to take the boiler rooms there, because that's really my limiting temperature. It might have the fan coils were designed for 160 for heating. Well, that fan coil still works at 125 degrees. It just doesn't put out as much energy. But remember our first set of slides where we had the renewables swathing through there, that 7,000 hours? Those are all the hours that were off peak. And it requires less energy to satisfy the load. On the cooling side, we're delivering fundamentally the same temperature as a chiller would. Okay? We can make ice with heat pumps, and so can a chiller. I'm done. You guys get what you want. Oh, one more.
One more question. If you get back to the 8,760 hours, about 15% of those, you either need additional heat or additional cooling, correct? I mean, in theory, if you were to take and put half the facility in the ground, would that offset that 50% requirement? And take advantage of the geothermal benefits?
Well, remember the rule is a 60-90 rule, or 50-90 rule. 50% of the load covers 90% of the hours. So that's probably what I would want to start looking at. We take a little bit of conservative because use of the buildings change. You know, it might be all office right now, but next week it's going to have a restaurant in it. So we like the 60-40 because it gives us a little bit of slop on either side. But, you know, it's always easy to add a conventional device. It's hard to add ground loops. Unless you're in some sort of an area like some of the things downtown Salt Lake City where we've got, you know, we've got a large apartment complex down there. It's got a condo complex. It's got 1,000-gallon minute water well. We could go draw another water well on the other side of our property. But generally, it's hard to add that renewable after the building is built. So you want to turn around and look at it for what you got, what you plan to be for the future. What?
What's the payback for a ground source pump type system? What's the typical time to payback? The one you showed in Mesa was like 1 year. can't be 50.
Well, that was for the central loop add-on. And that's what it was. The ground source system itself was designed to, it had to pay out in 8 years. So, can you add anything to that, Rich?
Well, we see 8 years, 7 to 8 years, real common. Especially if you could add like a Rocky Mountain Power incentive to it.
Actually, the stuff we're doing in Mason State, a good portion of it was, your firm was the mechanical engineers, the record of that.
What about residential?
Residential, propane, or natural gas, or electricity. It depends. Just so we get on resident. In today's day, in today's market, with the depressed price of natural gas, I'm going to tell you, my partner runs the oil and gas company, the other side of our business, and I run the green energy side. So we go through this. You know, I atone for his sins. He makes my retirement up until 2 years ago. The price of gas in the area went down so low. It's down so low now that we're barely able to produce. So under that scenario, we're seeing 10 years. With the federal incentives and the state incentives that are there until 2016, we can get 30% of the cost back. That brings it back to that 8 years. So in some of the northeastern markets where we were going against fuel oil and stuff, we're looking at 3 years, propane 4 years. And again, and some of the times are actually less expensive depending on how the house is set up and what it's designed, what altitude, and everything else. We're actually seeing the ground source system go in with its federal and state incentives less than a conventional system. So that's all that stuff is part of your life cycle costing. That's why it's so important to do that planning.
Is there a lifespan for a system like that for rusting underground? Is that
Well, the underground section is properly fused and tested, and stuff is guaranteed for 50 years. It's going to be a lot like the baby diapers in the landfill. That HDPE is not going anywhere. We had some trouble with polybutylene at the very beginning. Had a solar UV problem, but right now everything's high density. So ASHRAE says 22 years on the heat pump. We're replacing stuff in Seattle that was on water loops up there that were put in the late 50s and 60s. So, we're seeing some cases 40 years if it's treated properly. Again, that's the limiting. We have heat pumps now. They're called extended range units. They're good from entering fluid temperature 25 to 110. The old heat pumps choked at about 55 entering on the cooling, and somewhere around 85 or 90 on the heating. I mean, they choked, they locked up, lost compressors. So the new equipment and the new design of the equipment is helping a lot on that. Thank you for your time. I'll be here if anybody else.